Hello guys, how are you? Welcome to our channel Science Beyond Books, and I'm very happy that we are back with eighth episode of Science and Research Simplified. And today's episode is going to be very important and very interesting because today's speaker is a former scientist from NASA. He was working in NASA, and now he's working for European Space Agency, and he's going to talk about a lot of important stuff, including what is astrophysics, what are the different field in that, what scientists do, what kind of research basically do they do in this field, and if you want to become a researcher in this field, how you can become a scientist or researcher in this field. So there are a lot of interesting stuff we're going to talk about. Uh, so before so our speaker should be should be joining us in a moment. So before he joins us, there are a few things I want to let you know. Is The first thing is that if you are new to this channel, first of all, what you have to do is you have to press subscribe button, which should be next to you, and then you also have to press the bell icon. And once you press these two things, what happens is that whenever we do these shows, so basically we do this talk every Saturday, and we try to bring researcher every Saturday from all different field of science, and we discuss it in a very simple words, so that from a school going student, even the undergraduate student, they can learn from it, and they get a glimpse of what basically happens in lab, how scientists work, what kind of research they do. So this is a very interesting concept we do every Saturday. So first of all, what you have to do is just hit the subscribe button and press the bell icon so that you get notified that what will be the next talk, and you will be prepared for it. Also, if you are watching it on your mobile phone, or I suggest you that you try to use your laptop, because if you use laptop or television, it will be easier to follow, because we might use some presentations, we might use some images, and that will be very easy to follow if you're using a bigger screen. So I always recommend you guys to use a bigger screen if you have to watch this live show, so that you can go through the presentation, you can see small images or pictures we show on the presentation. So I recommend that you use that. But if you don't have laptop, that's absolutely fine. If you don't have television to watch the show on your television, that's also fine. All I'm suggesting is a bigger screen will help you to have a better vision of the presentation we do here. So our speaker is already here, and I think I'm gonna bring him on the screen. So I'm really delighted. I'm really happy that he's here. So for you guys, before I bring him on this show, one thing I want to tell you, that just share this live to as many as friends you can, because this is one of the best talk we're gonna do, and I'm very excited about it. So let me bring the speaker on the screen, and if you have any question, any doubt, ask in the comment section. There's one more thing, that if you want to come live on the talk and want to ask face-to-face question from the scientist, you can do that. All you need to do is just ask me in the comment section that I want to come on live and ask question. I'll provide you the link. So with that words, let me invite today's speaker, and let me have him on the screen real quick.
Hi.
Hi. Hi, how
Yeah.
are you?
Yeah, I'm good. Thanks. Yeah, thanks
I'm,
for
I'm
having
so
me.
Yeah, I'm so happy, and I'm so delighted that you agreed to come on our show and
Mhm.
share your research experience, and gonna talk about astrophysics, about the field, about the career in this field, and a lot of interesting stuff related to astrophysics. So I'm very happy that you are on my show. Thank you for joining us.
Yeah, no, it's the pleasure is mine, and yeah, of course. I mean, I will try to make it interesting. That is, I think, the most important part to me. That like whoever is listening, that they can gain some interest out of it. Yeah.
Absolutely, and that's the idea. And because astrophysics is something, many young minds, they always inspire to become astronaut, or they want to do rocket science, they want to study the universe. So I think for them also it's very great opportunity to talk to you, to listen your talk, and they can also interact. They can ask their question in the comment section, and we'll try to take as many as questions we can towards
Yeah,
the end of the
absolutely.
show. So
Yes.
before we start today's show, let me introduce our speaker. So today's speaker is Arkaprabha, Dr. Arkaprabha. He is from India, and he did his undergrad from Presidency College, Kolkata, and from after doing his undergrad from there, he moved to IIT Bombay, and he did his masters from IIT Bombay. After doing his masters, he moved to Switzerland. He did his PhD from Switzerland, and after doing his PhD, he got an opportunity to work in NASA, and he worked in NASA for a couple of years as a researcher, postdoctoral fellow. And after working there, he moved to recently moved to Denmark, and he's working in Neil
Niels
Bohr
Bohr
Institute.
Institute. Yeah.
Yeah, and that's in Copenhagen, right, in
Yeah.
Denmark.
Hmm.
Yes, so that's where he's working right now, and he works for European Space Agency. So he take care of some of the projects from the European Space Agency. So he's going to talk about all those stuff. So that was a very brief introduction about as a speaker, and it's wonderful to see someone like you, your profile is so outstanding that you worked in two of the top institute or top organization for space studies. So very congratulations for that.
Yeah, no, that's fine. Yeah. So, but yeah, thanks for introducing and thanks for inviting me to talk. And it's not like I'm someone really famous to not be here. I am very willing to come to talk to the people, and you are doing incredible work of connecting to students. And I had always been interested in doing that. So it would be nice, and hopefully today I'll be able to shed some lights on astronomy and astrophysics and what is it about, and in simple as possible. So I would share my screen,
Yeah, so
and
if you would like to put some presentation or something which we can start with, that will be very helpful.
yeah,
Yeah.
so share screen. And
So meanwhile, kids, ask your friends to join. And if you miss the live show, you can always come back to our channel and watch this show. That should be there. But ask your friend to join, subscribe the channel, and share it as many as with as many as students you can. Okay, so let me have the presentation on the screen, and if you want, you can go to the presentation mode.
yeah, I can do that. I'm thinking, will that be useful?
Yeah. So
Mm, okay, but I wanted to also have like you on the screen, not only the slides, because
no, no,
if
I will be on the screen. So if you go to the presentation mode, and when you
mm,
speak in the for the live session, I'm controlling everything from my side. So there will be presentation, and on the side, people can see you and me also.
okay,
But you will be in the presentation mode.
okay, yeah,
Yeah. So you can go to the presentation mode and just explain it, and on
hmm,
the screen, I'll control everything here. Yeah.
okay, super. Okay, so I would talk about infrared astronomy today, but before that, I would obviously try to build you towards the direction of how we have got here. Um, So to start with, I would like to first thank my supervisors who have I worked with, and so these are Isabel Churchneff and Ellie Dweck, and they are amazing people, and they have been so kind and helpful, and that I cannot thank them enough to be my mentors and advisors. So I begin. So I would like to say how is space science defined. Like, we are always fascinated by space science, and we always think that, oh, that is incredible to look at stars, but what is it about? So space science in theoretical terms is defined as in two parts called astronomy and cosmology. And though cosmology is also can be considered as a part of astronomy. So Astronomy is the study of stars, galaxies, clusters, whatever is present in the universe individually, and their relation to Earth. Whereas cosmology is the science which is the whole universe altogether and how it is evolving. So cosmology is considered to be a part of astronomy, which deals with the bulk properties of the universe, whereas astronomy is the individual properties of different objects present in space. So and then astrophysics and study of meteorites and study of different chemicals in space, or whatever you can say, are all parts of these things. So what is trending right now? Like, people are doing research. So what is the most interesting research that is going on, if you ask? So one of them, which is really big, is the gravitational wave detection, which is called the technology called the LIGO. And this is the detection of ripples in the space-time continuum. You may not understand this right now, but you may not have to. And this is interesting because this is an entirely new way of dealing astronomy, which I would talk about later on. And India is very much involved in gravitational wave physics, and there has been a lot of research going on, and there has been new detectors being built in India. So India is one of the forerunners of this field. And then,
Can I interrupt you? Just very
yeah,
quick question. So I know that there are two Lego situated in, where we test. I mean, so basically, Lego is a device. It's a huge machine which is situated in
yeah,
underground, and they detect any gravitational waves coming from any star or any,
mhm.
any Big Bang. I'm sorry, any like black hole create or
Signals, yeah, yeah.
yeah, anything. Yeah. So if a gravitational wave is traveling very far from very far, we can detect
Mhm.
this using this machine, right? We can detect a
Yeah, so
gravitational
the
wave in reality.
the most interesting part is the high resolution of these devices. For example, like, as I said, this is like a detection of the space-time continuum ripple. So basically, there is a slight change in the space-time continuum, which you can just visualizing, even if you forget a space-time. If you just visualize it as a wave, so
Yes.
something has happened, say, very far away, and its signature on Earth is even smaller than the size of an atom. So the wave that you are detecting here is only even smaller than the size of an atom. But what happens is that we have two very long detectors, like very long. I am talking in very layman's term, which is also I am also a very layman in terms of LIGO technology. But what happens is that you have very long detectors, and when the space-time continuum is this wave travels through that, so there is a difference in size that happens in the two detectors, because they are
Yeah.
so long
Yeah. The
that
distance
even,
changes because of the wave. Yes.
yeah, so
That can be detected.
and that can be detected, and the accuracy is incredible. Like, I mean, as I said, it can detect things which are even smaller than the size of an atom, which is traveling from like billions of light years away.
Right.
And that the accuracy is incredible. And also, what is incredible to this is that until now we had always visualized astronomy or space science as study of lights, because light is the only thing that carried information to us. But because of that, this is a second way which can complement the study that we do in astronomy, which we look at light to do. Whereas this is not, or study energy coming from different objects in space, whereas this is a different way of detecting the ripples in the continuum, and that can tell you similar inferences or complement what we do in astronomy. So this is, people have compared it as like sound. If light is to seeing, then gravitational wave is to hearing. So this is kind of something that people have been saying. And so this is a very new thing, and that is why this is incredible. And then, I mean, to move on, apart from that, what is more in trending going on is to look for planets and exoplanets, and to look for intelligent life in exoplanets, which means that, I mean, in layman's term, to try to find aliens, but in scientific terms, what we are trying to look at is habitable environments, like environments which are similar to Earth, like similar size or similar temperature and similar environmental conditions, or possibility of having water. So all these things have been is being studied, and a lot of government around the world is paying a lot of money to astronomers to look for planets which are habitable or which are similar to Earth. And if there is somehow we can find some signature of some life form, maybe intelligent or maybe primordial, but some kind of life form, if we can find a signature of that, that is a very hot topic in our research, and it is going on for last 10 years, and a lot of money is going into that. And then the third one is sounds boring but also very interesting in terms of computer technologies, that we are having so much of data right now from coming from different observations and telescopes. They are humongous, and we have no tools basically to deal with them and to intelligently study them. So there has been a lot of studies going on to build tools that we can actually accurately study the data coming from space, because the data we have is so complex that unless you have the right tools, we can easily have a wrong conclusion, and we want to avoid that. So the development of tools to deal with big amount of data coming from telescopes or coming from different space observations, that is one of the important things that will be going on for another 20 years maybe, and would be a lead research topic. But that's I don't want to go ahead of my topic, so let's.
So before you move forward, can I ask you a
Yeah,
quick question? So
yeah,
what
yeah,
are
sure.
the astronauts? And are they
Yeah.
different, or are they also astronomers, or they're
Okay,
different?
yeah. So no, okay. So astronauts are basically defined by people who are trained to go to space. So they are not necessarily astronomers, though there have been some astronauts who are astronomers. But so now, as you know, or as I should point out, that as I was working in NASA, I have seen that like the majority of the people working in NASA is actually engineers, and a major part of NASA's missions are actually dealing with satellites and building of telescopes and building of different like technological tools to study space. But majority, like 80% of the people working in NASA are engineers, and astronauts are most of the time engineers, and they are trained physically. So physical fitness and physically being very like active or very like, capable is one of the important criteria to become astronaut, because if you have to survive in space, you have to be physically that strong
True, true. You're right.
and enduring. So most of the astronauts are actually engineers, and they have training to deal with flying spaceships, or managing things over there, or repairing something which has happened in the International Space Station. Well, while some are also astronomers, who do fundamental research while being in space. But as I said, like the primary criteria is to also be physically very fit. So that is one of the very important criteria to become an astronaut.
Okay.
So yeah, so to move on, um, as I was saying, like in the previous slide, that everything in space is about light. So light is basically characterized by energy. So different energy, different light. I mean, in light particles or photons, if I may say so, are of different energy beams, and we can visualize a part of it, which is between 400 and 700 nanometers. Maybe many of you already know that this is the only region of the entire electromagnetic spectra that we actually can see. So to put that into perspective, this picture shows exactly how much this is. So this is this this swath of this small region that we can actually see, and then nothing else. The entire other parts of the electromagnetic spectra, which means that the energy that is being carried by any photon, which we can see on Earth, or which not see, I mean detect on Earth, they have spectra that could be X-rays, could be microwaves, could be infrareds. So my expertise in infrared, so I would talk about that. So infrared is something which is lower in energy compared to the visible wavelengths, just lower than the red side of the band. So to give an example, the TV remotes that we all have in hand, they are of radiating in the infrared wavelength. So we don't see that, right? When we just click the remote, do we see a ray going to the TV? No, right? Because they are producing something which is not in our visible range.
Range.
And yeah, so we are so I my expertise is in infrared astronomy. And so to add to that, talking about infrared astronomy is also known as something which is associated with temperature. They are also called temperature waves, which means that anything that has a temperature, could be Earth, as big as the Earth, could be as small as some molecular clusters, could be anything, but whatever is like a solid object which has a particular temperature does radiate in infrared. Like human bodies, we radiate in infrared. Anything, if you have a ball, if you hit that ball up at home, that would be radiating in the infrared. You will obviously not see, unless you really make it red hot or burning, you would not see the ball doing anything. If you take a football, or even like anything solid, take a rock for example, if you take a rock and hit that rock up in fire, you would not see the rock glowing, but it is still hot, right? So it will cool down at a certain time. So how it cools down is that it is radiating in infrared, because any solid object in the universe, it radiates in infrared wavelengths. That is how they are characterized. So I think I have made some kind of introduction to what infrared means, and then I would now go to infrared astronomy, and how did we actually like get here? Um, so we know a lot of things today, though even if it is very small, we do know things today, but it was not like this before. So what happened in history? Like if we look at the 100 years in the 18th century, what happened was, we were always doing astronomy. People were looking at the sky for thousands of years with whatever tools we have. Maybe we were using magnifying glasses, we were using naked eye, we were using handmade telescopes, whatever. Maybe we were looking at the sky for thousands of years, but all we could see is our visible band. So basically all we saw was that narrow 400 to 700 nanometer band that we all saw. So this is a picture of what we would see if we look at a certain region towards the sky, which is called Barnard 68 nebula. If we look at that, uh, this is what it would look like. So famous astronomer William Herschel had called this as like holes in the heaven, which means that he has coined this region he as like a void region, which is like a hole. And it was astonishing, or people were really wondering like why there are regions, and this is not the unique one, there are several. When people look at the sky, people used to find that there are certain regions which are nothing, like they were like just dark regions. So people thought that what happened there, like why is there nothing in there, whereas the rest of the sky is full of galaxies and stars and whatnot.
Yes.
So people used to think that for 100 years. Then post 1930, people started understanding that they are not actually void regions, they are not hollow regions, they were actually something there. And that is, there is like clouds of opaque objects, like clouds of gas and dust and things like that, which are so dense that they are actually blocking things from behind. So we are not able to see what is behind that because they are opaque objects. So from 1930 to 1960, these 30 years, people had been doing a lot of astronomy, but people always used to consider these objects like an annoyance, that, oh, I want to see something, but then there is this cloud in front of us, so we could not see something behind that. So this is a picture of the Eagle Nebula, which is a famous picture taken by the Hubble Space Telescope. And you see, these are the this structure is named as the pillars of creation, and this is just basically a gas cloud which is blocking whatever stars or whatever is there behind it. This is also a similar picture. It is called the Horsehead Nebula, and this is also a picture taken by the Hubble Space Telescope. And you can see that this black region that I'm pointing to, they are blocking things from behind. So this is something that people used to wonder, that like how to deal with it. Then post that
So can I ask a very quick question before you move forward? So the Hubble telescope, right? It deals with the visible light,
yes.
right? So it's just so it's like a regular telescope, like one I have here. As you could see, this is very preliminary one. So we capture light, and with the light we can, I mean, so the Hubble telescope has the huge magnification and resolution, so it can really go deep into the space and try to take picture of very far stars and galaxies, but it's still invisible, right? So you look at the light and take pictures. Am I right?
Yeah, exactly. It is
Okay.
visible wavelength, but it is
Yeah.
in the space. So obviously, what you will see on Earth would be totally polluted by the atmosphere, whereas in the space you do not have the atmospheric pollution, so you would be seeing things much clearer.
And that was the idea, to put it into the space and start
Yeah,
looking at the universe from new
yeah.
perspective. Yes.
Yes.
Mhm. Yep.
Okay. Yeah. So yeah, that is correct. And then to move on to actually getting into infrared astronomy. So until now, I was talking about how these clouds of regions were a difficulty for astronomers. Then finally, in 1960s, we started looking at space in infrared wavelengths, and we actually found out that there are clouds and there are like gas and dust, which are, what they are doing is they are not only blocking things from behind, but they are reprocessing it, which means that whatever well, if you look at this picture, there is a star behind this cloud, and the star is radiating in whatever wavelengths it wants to, and the wavelengths that are in visible regions, they are getting scattered away or absorbed completely by these clouds, whereas the wavelengths which are in infrared, they are actually getting reprocessed and transmitted directly to us, towards us. Or also, whatever light was there in different wavelengths, the cloud absorbed those lights and that energy, and then they re-radiated that energy in infrared wavelengths. Because as I was saying, that infrared wavelength is a characteristic, infrared radiation is a characteristics of dust or molecules or whatever solid opaque objects, and so these are similar objects which fall in that category, and so they are reprocessing the entire radiation. So to put that in numbers, actually 60% of the luminosity luminosity means like the energy that is coming per unit time, but in terms of energy I can say, like the energy coming from different galaxies, 60% of that is actually getting reprocessed by these dust clouds. So what we see here today is actually a product of reprocessing from different clouds. So if we know what is infrared astronomy, or if we can resolve infrared astronomy, we can actually find out what is behind that. And so once we started doing that, everything in this field became much more interesting, and we started looking at objects behind these clouds, and we also could find out signatures of objects which we never thought existed, because now we are looking at wavelengths where there is very little scattering, and we could actually see the light getting from the star to directly from us, or getting reprocessed and coming directly to us. So I have put the numbers of wavelength regions which are coined as near infrared or mid infrared or far infrared. These are just astronomical terms. You may not remember them just for the sake of the talk. And so I am trying to establish that, so how important this field has become, and also how important this discovery of these molecular and gas clouds in space, which is also kind called nebula when it is lighted up by different objects. So I have pointed out how important they are, and so let's look further into it. So now that,
So before you go to the next question, I can
yeah,
just take one question. So there is Ritika Jan. She is asking that. So
yeah,
does
yeah.
the light have a constant speed throughout?
Does the light have a constant? Sorry.
Speed.
Yeah, the speed
So,
is constant, obviously.
yeah, the
In
speed of the
vacuum,
light is
obviously, it has a
constant, right?
constant speed. Yeah, in
Yeah.
vacuum, yes, in
So
constant.
only thing
But
I
the
think you are
energy
trying to
is
convey
different.
is. Mhm. Yep, yep.
The
So I think
energy is
what you are
different.
trying to. Mhm.
Yeah, no, go ahead. Yes.
Yeah, yeah. So what you are trying to say is that when energy travels, what we
Mm.
see through the telescope is the visible light, and that the speed of the light is same, but the energy will change because when it get reprocessed from the cloud or other objects,
Mhm,
it could come in to us in infrared spectrum or some other
mhm.
spectrum. It depends on that which wavelength it is getting,
Yeah, yeah,
changed to. So that's why if we just rely on visible light, we probably miss a lot of information which is coming
yeah,
from the space. So we
yeah.
have to rely on some other method to if we want to know the entire spectrum, we also need to look not only as the visible light, we also need to look at infrared and some other part of the spectrum.
Yeah, I
That's
mean,
what I get from you.
yes, exactly. Like people are looking at all wavelengths. I am talking about infrared in particular, but people do X-rays. People do
Yes, yes.
try to look at some sub-millimeter or radio waves, and like every wavelength people are trying to look at. So what I would be talking about is typical of infrared wavelengths, and this is the phenomena that is like these gas clouds and what they do and what that leads to. Those things are very typical to infrared astronomy, and
Okay,
I
got
yeah.
got it.
So so far so good, that I have told that like it is very interesting to look at infrared wavelengths, and that can tell you a lot of information. So we would start looking at them, just putting up telescopes and detecting energy from there. Why not? So then came a big challenge. Like what we understood is that if you look at this the spectra on top, where in simple terms I'm just showing that absorption characteristics of water vapor and carbon dioxide in our atmosphere as a function of wavelengths. So if we look at that, the shaded regions, all the shaded regions in the pictures, they actually say that all these wavelengths in this region is absorbed by water vapor and carbon dioxide. So which means that a large part of the infrared wavelengths, so that is actually exactly here, and the infrared wavelengths that that the x-axis actually is pointing to, is getting absorbed by the water vapor and the carbon dioxide in space. So if we put a telescope on the ground, we will see nothing. So
Hmm.
nothing in the sense like minuscule amount.
Mostly, yeah,
So
mostly will be absorbed, and there will be very
yeah,
few information you can get.
yeah, so that is a huge challenge, and so people started putting up telescopes far up. Like there is a mountain in Hawaii, the island of Hawaii, called the Mauna Kea, which is very popular for astronomers because it has a very dry climate and it is also very high in altitude. So it has a very little water vapor actually polluting the observation. So there are telescopes set up over there. Then there is a mission called the Sophia Space Observatory, which is a flight moving around in around our Earth, and it flies in a very high altitude, and it has set up telescopes on that, and it is detecting data while flying very high. Same thing has been done with balloons. People have put telescopes in balloons and raised it up in the stratosphere so that we can record data from there. And the best case scenario is to put telescope in a satellite so that it does not have any interference from water vapor or carbon dioxide, but that is cost effective, so cost subjective. So these are something that people tried to do from the 1960s to 1990s in different ways to actually start looking at into infrared astronomy and signatures from these things, these molecular clouds or nebula or many other things that I will talk about next. So then as I have established that like we can have a lot of information from looking at infrared wavelengths, but then what do we mean by looking at? Like what do we see? We cannot see it indirectly in our eye. So what we do is we look at the spectra. So in simple terms, I have tried to explain what a spectra is. And that is, if you look at the figure on the left, so spectra is essentially can be differentiated as emission spectra and absorption spectra. So emission is something when something is emitting light or some emitting energy, whereas absorption is something when it is absorbing it. So the on the left is an spectra of our common light bulb, like the ones which had this warm yellow light, which was very common in our houses in the 90s. So that warm light bulb is basically emitting energy, and this is the spectra of that. So this is basically the emission, and these lines that we see is coming from the ionized mercury lines. So the from atomic physics, we actually know the energy levels that certain elements would be emitting or absorbing energy at, and by looking at that we detect whatever is present in there. And so this is an emission spectra. So it is upwards, you see. So upwards means that it is positive, which means that it is producing energy. So that is called emission. Now, if you look at on the right, you see that the lines are downwards, which means that it is actually absorbing energy. So it is negative, so it is downwards. So which means this is a spectra of water vapor and oxygen, what it does to our sun, radiation from sun or the sunlight. And you see the specific lines of oxygen and water vapor that we can see over here. And this is called an absorption spectra. So this is just an example of what we see. So when we look at certain objects in any kind of astronomy, we try to look at the spectra and try to resolve the at different wavelengths, what is the amount of energy that we have received. So spectra is the amount of energy we have received at a particular wavelength from a given object. That is the simple definition. But to make it a little more complex, so you see on the right, on the left, this figure, which is that which says that there is the absorption line which is going downwards, emission line which is going upwards, which is what I was explaining. But there is also a continuum, which means that they are not, this absorption line and emission line is not on a flat surface. It is on actually on something which is continuous. And what is the continuum emission? Continuum emission is basically a kind of emission which does not follow single lines, like they are not discrete lines, as I was saying. So normally gas particles, when ionized or when heated, they have a discrete emission. That is basically from atomic physics, we know exactly in this wavelength this element or this molecule is going to radiate. Whereas continuum emission is a characteristics of solid particles. So like anything which is solid, as I was talking about temperature radiation. So the radiation from any solid particle is only dependent on its size and on its temperature, given that it has particular absorption properties, which is depends on what material it is made up of. So those are the solid state properties of that material. But based on that, it is only a function of the temperature itself. So that it does not radiate in discrete wavelengths. It has a very continuous nature. Now, depending on the temperature, it can be high. It can have a huge bump in the high energy regime. Whereas if it is low temperature, if it is a cooler object, it can have a bump in the low temperature or low energy regime. But it is always a continuum radiation. So that is what I am showing here. And also in the picture on the right, I am showing the two continuum absorption features of a carbon dust, which means that like a cluster of carbon present in space, and two different sizes. So depending on the different size of this cluster, they have different absorption absorption features, but they are still continuous. They are not discrete features. So continuum is a particular characteristics related to solids, and this is very important in terms of infrared astronomy, because lot of things that we see are actually radiating in continuum, because infrared is particularly made for that. So I have established that there has been evidence of large clouds of gas and dust in space, and I'm saying dust and dust. I should need to coin this again. So dust is something which is a chemical compound which has similar dimensions to what we see as dust in our own atmosphere. And so dust grains that is present in space is actually has similar dimensions as of what we have here. And so that's where the term has come from. And they are simply chemical compounds. They can have different chemical signatures. They can be made of silicates, they can be made of carbon, they can be made of iron compounds. They are basically chemical compounds which has been formed in space. So what I am trying to explain in this slide is that in space there has to be certain environments which produces good enough physical conditions, that is temperature and densities, so that the gas is at high density enough that the chemical reactions can make chemical compounds. And in addition to that, the temperature of that has to be also high enough so that lot of chemical processes which have activation barriers, which I think many of you are already familiar of, that chemical processes sometimes or many times need energy to continue. And if it is a very low temperature environment like space, like in space most of the environments are very low temperature, so in those environments you cannot actually have any type of chemical reaction, because you do not have enough energy to actually activate molecules or activate gas particles to react among each other. So the bottom line is that there has to be some kind of environment in space where we can have chemical reaction producing chemical compounds, and which leads to formation of dust. And this is called cosmic dust, which we have seen evidence of being present in these clouds and that is what infrared astronomy deals with. And so the puzzle is, where are these environments? So like as I said, that in normal space, like in the medium, interstellar medium, it is, there is no environment such as that, because there is very low temperature, very low density, nothing happens over there. So while probing through that, we have actually found out there are certain regions which provides an environment like that only for a very short amount of time. And one of them is the supernova ejecta, so like the exploded materials coming from a supernova. So I would come to supernova now, I'm not leaving you on that. So just to say that, so the story here is that there are very few environments which can provide certain conditions which are conducive enough to continue molecular and chemical reactions in there, and which are producing this dust. And there is a lot of dust. So to put that in perspective, it's not a small event. The whole galaxy is full of molecules and dust, and this dust has to come from somewhere. And that is one of the big puzzles, which is also one of my research topic, that the origin of cosmic dust, where it is coming from. So I'm now moving on with this conviction. I'm showing you some pictures of what the chemical structure of the dust particles would look like, and they're different chemical forms of made of silicates, made of carbon, made of magnesium, all these things. The common feature among all of them are that they are energetically very stable, so they do not break down easily in small, because in space there are so many things happening that if you are not stable enough, you can easily break down to smaller particles. So these particles are so strong that they can act as a seed means that they do not break down themselves, and then when there are similar particles that come together, they can grow in size and they can become much bigger in size. So this is what we are defining as dust grains. And the interesting part of it is how much you dislike this and how much you think that, oh, that is boring, it is not colorful, we do not see pretty pictures. The story is that everything that we have around us is made up of this star dust. Like every planet we see in the solar system, even us, the calcium in our bones, or the iron in our blood, or anything, your chair, your table, your glasses, everything is made up of something which has originated once upon a time in some kind of stardust, which has been processed over time, over and over again, and built this earth that we are living on today. So the building block of all the planets, including our earth, is this molecule and dust coming from some supernova or some objects like that. So that is the interesting part that we cannot ignore. So where I am, I
Yeah, yeah, yeah. So
I
yeah,
think
we can hear you.
Ajit is not in.
We can hear you.
Yeah, you can. Okay, that's
Yeah,
good.
yeah.
Okay, that's super. So I have, so basically that is where we are at. I'm running pretty late. I would make it faster. So so these are all abstract, what we were talking about until now. But is there anything that on Earth we can relate to that? Actually, there
Mm.
is. Like, there are meteorites that we can have on Earth, which actually have evidence of presence of these dust grains from space, which meteorites have carried onto Earth. And to show you today, actually, I have borrowed one sample from our lab. And so if you look at this thing, so this is a meteorite sample which has been collected from the Atacama Desert and in Chile, and it is made up of iron inside with a course of silicate surrounding it. And if you make a cross section of this, so actually I have another piece which is a cross section of this thing. So if you look at a cross section of this meteorite, you will actually see that there is signatures of silicates. Like, you see that there is small dots around there, and they are signatures. Basically, silicates are kind of glass, so they are different type of glass structures that is inside there. And this was on Earth from the Jurassic time, like from the time of dinosaurs. And this is something which was there when the solar system has not formed yet. So there are evidence of molecules and particles inside this thing which was there before the solar system has formed. So this is incredible that you actually are holding something in your hand which was present before the earth was formed in some way. Not everything in here, but there are some evidence of something inside this which could have formed during a time when the earth was not formed yet. So this is a sample of meteorite, and this is very heavy. I mean, I am holding it in two hands, and this is so small. And there is no rock on Earth which is so heavy. This density is almost 6 gram per cc, whereas rocks on Earth are maximum 3 to 4 gram per cc. So this is pure iron surrounded by silicates, and this is coming from some time which is before the Earth was formed, and that is incredible. And this is an evidence of what stardust or things can be
That's
related.
that's really outstanding to see. I mean, I have not seen it live, like
Yeah,
a particle which is coming from outer space or not
yeah.
from the solar system. So, do we know
I
the
mean, this is
origin of?
from the solar system, but it
Also,
has
it's from.
evidence of particles embedded in it because it was there when the sun was formed. So it was,
Okay, got it.
so whatever was there before, it has some things embedded inside it, and then it
Okay, so
fall
it
on.
carries particle which was like prehistoric, like really
Yeah,
old
yeah, it's called
stuff. And
pre-solar. So it's called
yeah.
pre-solar particles. So before the solar time. Yeah.
Uh-huh. Uh-huh. That's interesting. And with that, can I ask? I mean, I was reading one of the news that I think China or Japan they managed to collect some sample from the meteorite which was outside the. Uh, I mean, it was like they were able to send their probe to the meteorite and collect some sample and bring it
Yeah, so
back
that is like a
because when it
comet
comes,
landing. I think you are talking about the comet
yeah.
landing. Yeah, so
So
there,
basically, yeah. Yeah, they
Yeah,
basically they were able to. So because when this meteorite come into the Earth's atmosphere, they get polluted or they get changed
yeah,
because
yeah, yeah.
there's
And
a
also
lot of
most
heat.
of them get
Hmm.
burnt off, and not many actually fall on Earth.
Yep,
Many
yep.
of the things, asteroids, that are actually burned off. Whereas if you go to comets or even in moon's surface, like when the
Hmm.
lunar missions were going on, people used to
Hmm.
carry a lot of rocks from moon, and those rocks, many of them were also coming from like these asteroids that has fallen on the moon, and or meteorites from the moon's surface. And so there has been a landing on not one but couple of missions, and then people have collected samples from the comet surface, and that is also a similar thing like that I was showing here today. And
That's true. Yeah, I was just
this
reading that
this
that
has
they managed to go there and bring sample, and recently they received like they sent it like a couple of years ago, and recently
Mhm.
they got the sample on Earth, and now they're gonna
Yeah.
study it. Yeah.
Yeah, I mean, I'm not yet, I do not know yet that it has reached on Earth or not, but they were collecting at it definitely. And yes, that is like incredible to actually put things in perspective, because all I was talking about is mostly abstract. But
Mhm.
while if you have something in your hand, then you
And
totally
you
go
look
to
at it.
a
Yes,
different
yes,
world. Yeah.
yes. You're right. Yes.
So let's continue. Actually, I'm pretty late, so I would
Yeah.
continue, and I would try to skip a few things and go
Okay.
to the interesting ones only.
Okay. Sure. Sure. Sure.
Yeah. So where am I? Should I start sharing the screen again? Mhm. Okay. Yeah. So I'm going to the full screen mode, and yeah. So this was what I was talking about, and I will skip the life cycle of stars because I can do that without this. And so I was talking about supernova before, and I was telling that supernova explosions are one of the sites where we actually see formation of molecules and dust particles. They produce environments like that. But what is supernova explosion? And so, in simple words, they are the end of life of stars, and they are really bright objects. Like they are one of the brightest events in the universe, so much that they are almost like a billion times brighter than the sun. And that is incredible because the amount of energy that they can produce is so humongous that there is nothing on earth that I can compare it to give you a reference scale. So even further, like let us discuss what it is about. Like say there was a supernova that was observed in February of 1987, and it was in the galaxy Large Magellanic Cloud, which is about 160,000 light years away from us. And this supernova was named as supernova 1987A based on the year it was detected. And it was so bright that actually it was visible in our naked eye at some
Mhm.
points, whereas like it is so far away compared to like the planets like Jupiter, Mars. They are so close by, and we most of the time even like they are so faint. And whereas this object was 160,000 years away, light years away, and when it exploded, we could still see them with our naked eye for a few days. And also to put things in perspective, to say how far away they are, when the star actually exploded, we were in the caves. We did not know how to wear clothes. So I had put a picture of the caveman, the Neanderthals, uh, and that is how we were. And at that time when the star actually exploded, and the light has taken 160,000 years from that star to reach here today, and we are observing it today 160,000 years later in bright light. It was so bright that even today we could see that, which has happened in that time when actually it happened when we were in the caves. So you can now understand the perspective of how far away it is and how bright it could be.
So what happened to the material of stars when this explosion happened?
Yeah. So So that is what and everything boils down to. So like the star has exploded, so then what is it about? So to explain that, it I would go a little bit onto how we have come here, because in simplest possible like words, if we look at this picture, this is a cosmic time scale. And we are here, if you look at here in the red, it says present day, which is 13.7 billion years from the time of the Big Bang, when the universe was formed as we think of. And then there had been several phases of formation of galaxies and several phases of stars getting destroyed, and then they are forming these molecular clouds, and then they are forming another galaxy. So this is a cycle that is going on for years. So how we have evolved over time in terms of the materials that was in the star is like this. When the first stars were formed, they were huge in size. They were like 200 or 500 times the size. I mean, they are not even the first stars, they are the second generation stars, but they were very very large. And they were mostly hydrogen and a very little bit of helium. Then they died, and then we have a new branch of stars formed. And what happens is, when one star dies, there is so much of energy in terms of supernova explosion that is generated, that this supernova explosion leads to the elements like hydrogen, helium, lithium, or other elements to go through a process of nuclear burning, which is in other words called nucleosynthesis, which means that they go through nuclear processes to produce new elements. So that is how elements are formed. Like today we have 118 or 120 elements that we know of on Earth, but they initially there was one hydrogen, then there were two, and then slowly through these nucleosynthesis processes that we have today ended up in 118 or 120 on Earth, and there will be more. Like when this generation of stars that we see around us will die, they would also produce new elements or new metals, and then the atomic number will go up further. There would go up to 150, 200. That will continue for billions of years. And so coming back to what happened to the materials of the star, what happens is that when the star has exploded, this nucleosynthesis happens, and that leads to the production of new elements. So this picture shows how hydrogen leads to production of helium, and this is only possible in very high temperature. Different reactions needs different kind of conditions, of course, but to generalize, you need very high temperature to actually tamper with the atomic bondings and actually go through the nucleosynthesis or nuclear burning processes to form new elements. So helium, this is how helium was formed, and this is how everything through different nuclear channels, everything that shown in the periodic table in here was formed. So here we have until 118, but there would be new elements formed in the same way. So supernova is producing new elements when it has exploded. And how is that helpful in our perspective? It is helpful in terms of the fact that when you have new metals, you can form new more and more molecules and dust particles, because you have to conserve things, right? You do not, if you do not have any new particles coming out, then whatever amount of molecules you have would be either destroyed or formed, but you cannot increase the total mass. Everything is conserved. But once you are forming more and more new elements or new metals, then what happens is the efficiency of producing the molecules or producing these dust particles, which would later on produce planets, the efficiency goes up. So this is how the supernova explosion leads to formation of new elements. Then the new elements leads to formation of new chemical processes, and the new chemical processes gives you these dust particles, which are the seeds of planets that we live on today. So just a picture. I'm nearing the end of time, and I would not try to drag you too long, but this is a picture of how models. I am a theoretician, so all I was describing was in terms of theory and how theories or models are developed. there are several strings that we need to attach. We need meteorite samples, we need observations, we need chemists to tell actually how these particles would radiate, how, what are their internal properties. We read mineralogical evidences or data to model things. All these things come together when you form one single model.
Makes sense.
And sums up to this is the simplest possible picture of elements going towards larger clusters through several processes. As I've written, like there are 5,000 different chemical processes which acts to form these grains, which ultimately may look like this or down here. And this is called cosmic dust, and this is one of my research topic of how the cosmic dust, this is my main research topic, that the origin of cosmic dust in supernovae. So once we can find that out, there is a way to understand how planets were formed and where we have come from. So this is what the motivation of the research is. So then what are the challenges like we face today? And um, I have already pointed out some of them, so I would be quick. And the main challenge is that this is very abstract still. Even if we have described infrared astronomy and all that, the objects that we view, they are so far away that there are several times, or oftentimes what happens is that we only have one point from one galaxy, like one data point, and that is all. There are so many stars, there are millions of stars, there are millions of planets, there are black holes, there are so many things in a galaxy, and we have one data point representing everything in the spectra, and we have to determine things through that. So how inefficient it would be then. So we are
Yes.
so much limited in terms of how difficult it is to actually look at. And infrared being low energy, it is more difficult, because lower energy, it is more difficult to look at. If it is very high energy, then things are easy to see. So in terms of that, and in terms of computational powers, if we actually want to simulate something or model something exactly how it happened on space, this is so detailed that we need computational powers that we do not have right now. So we cannot form models which are accurate to the real life. We can only make like approximate models to mimic what is happening in space. But in space, things are so high energy or so robust that we do not have computational power to actually look into that.
But in future,
And
maybe we might have, because even the computational power, the technology improving us in a high
yeah,
speed, that
everything
IR
includes.
spectroscopy will improve, your softwares will improve, the capacity to store data, process data will improve,
Yeah,
and that will help us to get a clearer picture using
yeah.
these techniques.
Hmm. Yeah, definitely. Yeah, that is the future. So one of the to end with the to look at a brighter side. So this is a picture of the James Webb Space Telescope that was under construction in NASA, and the construction has now ended. And this is a picture of the mirror. You see the mirror. So the larger the mirror, the higher the resolution would be. And so this is a huge mirror, and there has never been any space telescope which is so large. And Hubble has already taken so many pictures. We all see, like any picture, mostly if we Google pictures of space, whatever we see, 99% of them are from Hubble. And Hubble has a 7 feet large mirror, and this one is a 21 feet diameter mirror, and it will look in the infrared wavelengths, and it is going to be launched in October 2021. And this was NASA's main project along with several others, but in terms of spectroscopy or infrared astronomy, this was NASA's main project for last 20 years almost. And when I was there, I was working with people who are doing this construction. I mean, I'm not a experimentalist. I do not work on constructions. I'm not an engineer as well. But many of my colleagues were part of this project, and were trying to working on the construction of this thing. And
So
this telescope. Yeah,
yeah, just to put this in perspective for viewers who are
yeah,
not aware of this telescope is, so we already have a Hubble telescope, which is huge telescope in which is uh, outside our atmosphere, and which is
yeah.
in space, and it takes a lot of beautiful picture, as you are mentioning. But now we
Mhm.
are planning to put another telescope which is much more powerful. It has much more bigger mirror, so it will have more resolution, it can collect more data, and we'll have a
Yeah.
all
No.
different perspective altogether once this is functional, once it's situated in the space and start taking pictures,
Yeah,
right?
absolutely. No, no, there are several space telescopes, not like only Hubble. Hubble is the most efficient one in the optical range, and we like that because we like the pictures that it takes. But in terms
Okay.
of, so
Also, there
there
are
are
many of
several,
them.
like hundreds of space telescopes. But
Okay.
this would be the strong, largest, and the most powerful one until now. And
Okay.
there would be no space telescope which would be even closer.
Mhm.
and uh,
Mhm.
and because it has the infrared capabilities, as I was explaining, it has the power to actually look to the early universe, because a lot of lights coming from the early universe time, from the time of the Big Bang, they are getting reprocessed by the clouds or other objects while coming to us. And also there are other reasons why infrared would be very convenient to look at early universe. And because this has the capability to look in the infrared, this would give us informations like never before, and we would really look forward to it if the launch is successful. The launch is expected in the end of this year, and it has been delayed several times, so we are skeptical that everything would go all right. But if it does, then it would be incredible, no doubt about that.
Absolutely.
Yeah. So I have spoken about everything that I wanted to, and
So,
so
yeah, so there is, if you want to come to the presentation, you can remove the
yeah.
presentation mode and you can come to the live.
Yeah.
Yeah. So, is there any other main focus of NASA these days apart from this? This is the
Obviously,
main.
no. This is no. I mean, this was so. As I was saying, NASA is very much into engineering, right? So NASA's focus is always remains on building satellites. So all the satellites do not have telescopes, right? Satellites can carry like the GPS satellite, which does the mapping of the regions, or the Google maps that you see. They are all in different satellites, and there are so many satellites moving around. And all the satellites only, like I mean, I do not know the number, but I am assuming even less than 1% of the satellites are actually doing some research in with having telescope capabilities. I might be wrong in this number, but it is something of this ballpark. So there are so NASA has done lot of always doing lot of engineering of satellites, and in the space station what they are working on. And the fun part is that, like, a lot of things we actually nobody knows, because most of the places are not open for even workers to get access of. Like when I worked, I had access to two buildings out of say 20, because many other buildings, if there is something confidential have there, then they would not access. They would not let anyone to have access. But the fun part is that, I mean, the James Webb Space Telescope, as we said, this was NASA's next big mission after Hubble. So it is dedicated to replace Hubble. Hubble will not work, I think, after mid 2030 or something. Hubble will stop working. So, if I'm
Yeah.
correct, but
Yeah.
then this would remain there, and this would
Next
be,
couple of years. Yes.
yeah.
So that was a really really outstanding presentation, and I'm very sure that our viewers learned a lot. So before we end our today's session, there are a few more questions I want to ask you apart from research. The first question we want to ask you that what motivated you to become scientist? How you came in this research?
Well, for me personally, like I was very interested in physics, and when I was leaving my school, mm, um, I was pretty sad. I would say that I would not be able to study more physics or solve more mathematical problems. It sounds very funny or like cheesy to say, but somehow I actually liked looking at things mathematically, because in other fields or other subjects when I studied, I could not like coin things in terms of mathematical equations, whereas in physics I could, and that was, I had a very fond interest towards it. So I went to physics, and then I was actually doing good in nuclear physics and astrophysics courses. So I was like slowly getting, so to be honest, I to be like clear to also the viewers, I want to say that like it's not always so, like for example, as you heard my talk, even if you people when think of NASA or astronomy, it's most like telescopes and discovery of this, discovery of that. Whereas what I talked about is mostly just pure physics, right? There is nothing much than
Yes, you're right.
so so in terms of that, like even when I was drawn into astronomy, I was more drawn into the physics part of it, and I hardly knew much of the details of what supernova is, what stars are, because they are so detailed. You cannot actually know so much that you can love it. You can be fascinated that, oh, there is a bright star, but you cannot know so much without really going into that, so that you are fascinated, sorry, you are like interested to learn more about it. So I did not know much about those things, but I knew that I mean, the mathematically solving problems which are related to space was something which interested me more, and I'm still doing that. I'm trying, still doing like pure physics and applying it in astronomy. So that is how my
Absolutely,
research is. Yeah.
absolutely stunning. So one more question I want to ask. There are many students who do not like mathematics or physics for that matter. How how they can fall in love with mathematics or physics? It's a very basic question. Like it's not necessary that everyone should fall in love with mathematics or physics. They can love whatever
Yeah,
they
yeah,
like,
yeah, yeah,
even
yeah.
art or science or painting, whatever it is. But if you want someone to fall in love with mathematics or physics, how they can start looking at it?
Hmm. Yeah, I mean, it is true that it's very. So I would say that the way, if you really want to motivate yourself, one of the thing is to look at the objective part of it. So in terms of physics, it is very easy that like uh, you have to forget the exam part of the subject, and you have to really look into the day-to-day application of physics that you see around us. So that also was how I got into it. Like when you give exams, like our entire system in India is based on evaluation of your how good you are, and that's it. And then when I was in college, somehow I could manage some time just to myself, and I could explore things in physics by reading things and by knowing things without thinking of how to remember this for the exam. I really did not. So most of the time when people are afraid of some subject, that means that they want to learn this subject for the exam. I mean, it does not matter, it will never matter. And even if you do not like that subject, and if you do not do good in that subject, does not matter at all. If you are not good in mathematics or not good in physics in exams, no harm will happen. You will still shine in life, you will do good in life. You have several fields in life that you can do good it. But if you want to like something, you have to remove the exam part of it. You have to look at what you see around us. So physics has this amazing capability, right,
Yeah.
to
So I
explain
think
everything around us. Yeah.
so. I think what you're trying to point is we have to be more curious, and when we are curious to know why we see this, why this happened, why that happened, see things around you. Like if you any small thing, and try to ask question that why it's happening. And when you start asking these questions, most of the answer comes from physics or chemistry, because you see physical world, right? You
Yeah,
see whatever
exactly.
you're seeing around, whether it's electricity, it's magnetism, it's heat, whatever it is. Like if you're using your microwave, ask this question: what is microwave? Why it can heat your food really fast? Like when you heat your food
Yeah,
on gas, it
absolutely.
takes like 15 minutes. When you put it on microwave, it takes 20 seconds. Why?
Yeah.
If you
Hmm.
start asking these questions, you'll start looking at the answers, and when you start looking at the answer, you'll find the logic behind it, and that's where you will start
Gain
falling
the
in love with.
interest.
Yeah, you
Yes.
will develop your interest.
Yeah,
So
that
I
is
think that's what you are
absolutely.
trying to say, right?
Yeah, absolutely. That is the point. Like, you do not want to fall in love with some subject just for the sake of it. It's like
Yeah.
if you see something around you, and if you can ask the question in your mind, that is enough. You don't no need to do anything else. That is the curious part of it that you said. Yeah.
Okay, so I'll take one more question, and that's a very big question. So, what do you think should be the moral responsibility of the scientist? Like being a scientist, what do you think about it?
Yeah. So that is something, I mean, really big, and we have overshoot the time, so I would try to brief it as much as possible. So I have like several points to get into that if you ask me philosophically. So what I want to say is, one is that when we do science, or when we look at science in terms of basic fundamental science, what we think of it is like, okay, it is something that we have to read, and we have to finish this in terms of the syllabus. But fundamental science is something that is actually a type of exploration which I do today without knowing what would come out of it. Like when, like as for example, who invented the cells did not know that we would be modifying the DNA today, or who invented, say, atoms, would not know that the atomic levels can be tempered in quantum technology, or who invented metal elements, they did not know that those elements would be used to build computers, or metals, right? So people do not know that. So what was the moral behind them? So like, they had this creative freedom to explore things without a cost effective part of it. So in all other fields, the issue is that whenever you want to be creative, there is a cost associated with it. So if you want to explore something, there is some cost associated with it always. But this fundamental science or scientists has this huge advantage, which we often forget, that we can be creative without being cost effective. Like we can, if I try to solve a mathematical equation in a new way, then nobody would be, say, like, there is no harm in trying that, and if I succeed, I would never know how that would be utilized. But maybe 100 years from now, there would be a certain device or certain instrument which would be built based on how I solved this mathematical form in a new way, right? So
Mm.
this is the type of creativity that only the scientists have the freedom of, which, because if in any other field, if you want to be creative, you have to spend that much of your time and that much of your resources to be creative, whereas we are encouraged to become creative, right? So
Yeah.
that is something that people should look into, and that is what the motivation or moral of the scientists are. And to quickly point out something else that is also like deeply to think about, and but that is, the point is that I think as scientists or any educated person has a moral responsibility to look around you and to educate everyone around you, because there is a term, there is a like a phrase which is as goes as, you are as you are as educated as your neighbor, and you are as smart as your mother. Which means that, like, if you are not part of the society, if you are an educated person living in a surrounding which where people do not know to wear mask when there is COVID, then you are not educated also, because you are a part of the society and you are contributing every day to be a part of the society where you are
Yeah.
living among the people who
True.
who you laugh at. Like, we have this elitism of education that we laugh at people who do not know things. So when Donald Trump becomes president, we all became internally happy that there is some stupid person who is talking stupid things. And being an educated person, all educated person were really having fun of that, because not thinking that actually we are the person who have created someone this stupid to become a president of some country. Also, when person who does not wear mask and go out to the road and say that I would not have coronavirus, we have also created them. Because when we got educated, when we were in school, we were always taught that you learn and become better than others. but we should not be better than others. We are here to make others better, right? So
So that
the,
as a community, as a whole, we
yeah, we
progress,
have to work
learn,
on that, right?
and
Yeah.
the entire society has to be enlightened. Yes, you're right.
Yeah. So that is something like, it is a very philosophical thing to say, but since you gave me the platform, I
No,
just
no,
took
no,
the
no.
liberty.
You are rightly pointed these things, and this is very important to hear and know these perspectives. Pretty much important.
Yeah.
With that, can I just take one or two questions because I think we are running a little
Yeah, we are
late.
pretty late, but
Uh,
yeah,
yeah.
definitely. I mean, I'm
Yeah, I
fine.
can take, and you can just give a quick answers to these questions. So there is one girl. She is, I think, Ritika Jain. She's asking, "Do you have to be American to come to NASA?"
No, but no, not at all. I am not American, but you have, if you want to have a permanent job, like a because NASA, all the NASA scientists, like my supervisor, was a well, like a government of United States employee. They were employed by the government of United States because they were civil servants, whereas
Hmm.
all others were researchers. So researchers can be of any nationality. There are few countries which does not include India, but China is included, Pakistan is included. There are few countries of whom the people would not be able to employed in NASA. They do not allow people from those countries to enter NASA. But Indians can work at NASA. They can be researchers, but they cannot work as civil servants who are the permanent employees, who are employed by the government of the United States, and they are like the IAS officers, the same status of the IAS officers or things like that in India.
Okay, so we'll take another question.
Yeah.
Smriti is asking, does the universe look the same as we look at the picture? Does it look beautiful as or compact with the different element? How would you define it in layman terms?
No, I mean, obviously, we have seen the universe in the pictures, mostly from Hubble's pictures, and those are not real pictures. Those are colorized by to make things like, for example, they have, it's not randomly colorized, but they have say chosen some gas and made it some given color, and then they have chosen some other gas and then they gave it some other color, and so all these blue, red, green things that you see is not real. They are colorized to make it visible, but unless you colorize that, you would not able to see anything. So the universe is not as beautiful if you compare it with those pictures, but universe is incredible. Like, there are so many things that happen which is beyond our imagination, so that itself is incredible. Like, you would never know. And today, like, I am like just like a junior most astronomer maybe, but even if the astronomy field has been so vast, you would wonder, like, you would be surprised to know how little we know. Like, we almost know nothing. Like, we just do abstract ways of finding answers, and we just try to back calculate things to find answers, because we actually know nothing. It's so vast that we actually know absolutely nothing of it.
I'll take two more questions, and then
Hmm.
we'll wind up today's talk. So there's Shashank Anand. He's asking that, can you please let us know the method used for simulation? Sorry, uh, yeah, simulating the space exploration process.
I don't know. Space exploration process is, I mean, it's a broad term. I
So yeah,
don't.
yeah. So it could not be from your area of expert, but because it's
I
we
mean,
have
uh,
yeah
s-
general.
so similar to make it fun. Like, I can tell you that when the first man landed on the moon in the Apollo mission, like, the technology that they used for that is is much lesser than the Casio calculator that you used in your board exams. So the Casio calculator that you carried in your board exam, that is much stronger than the amount of technology that was used
They
for
carried.
the Apollo mission to land on the moon.
Like that is something really surprising. Even when I look at those videos, and we had technology to send people there, and even before Apollo 11 happened, like we already had unmanned mission when we try to go there, come back from their orbit, and then we're able to do all those exploration. So we had technology to send people, bring them back. but these computer and electronics, I think, were not that
I mean,
developed.
no,
Like,
no, we are making it more accurate. Like now we are going to space station every regularly, like every year people are going to the International Space Station. And so we are making it more accurate. Obviously, there were a huge uncertainty related to that, and we had to trust human instincts. Like when someone was flying it's same as cars, right? So the satellites were mostly flying on autopilots, whereas in the first generation they were men who were actually operating them. So the amount of accidents have some result on that when you are actually using machines to flying the plane, but the plane still used to fly then and now. So it's similar, like it has become more and more accurate and streamlined. But yeah, I mean,
yeah.
no, technology is good, no doubt about that, because without that there would be missions that would fail, and there would be a lot of things that would not be.
That's true. So there is Jagdeep Singh. He's asking that how IR telescopy or telescope deal with
Telescope.
radiation pollution, like radiation from nearby objects such as sun or planets.
Yeah, so they have shields basically. Like it's difficult always. So if so, what happens is in when there is a space telescope, and it would not take any observation when it is. So the satellites are going around around the Earth, right? So there would be times when it would be facing towards the sun, and uh, at that time, obviously, you cannot observe anything behind the sun. And for other times there are shields, there are huge space shields. If you just google James Webb Space Telescope, that way I was showing, you will see the sun shield that they have built. They have a huge shield, so that when you are observing, say, on this side, you will be shielding the sun from that side, and on the other hand you will never be able to observe something which is being blocked by the sun. So that is how it is. but
So
but
I
since
have.
we are monitoring which way to look, so obviously we are always pointing away from the sun and trying to record data from that direction. Yeah.
There is one more question. I don't know whether it's specific to your area of expert or not, but I can just throw this question. So there is a question: if charge
Charge
in,
is an intrinsic
I can
property.
see it in a very
Yeah.
small screen. Let
If
me put
charge
it
is
on.
an
Can you
intrinsic
read the
property
question?
of matter, then how electrons and protons have the same magnitude of charge, although they have different masses?
So I think it's not much related to your work. So you can choose to skip this question if you want, but if you have any idea, you can.
I'm thinking. I mean, but I mean, I should talk to the whoever has asked the question, because what is it to do with intrinsic property of matter and the difference in mass? Because they are made up of different quarks, and
Yeah, I think it's more deeper than, because I think we are getting more into the quantum physics and try to understand that how charge uh, as a whole unit, we can compare the unit of charge, like, there is
yeah,
one
yeah,
positive charge, one negative charge on proton electron, but the mass is different. So I think
yeah.
charge is one different property and mass is different property. Mass is related to energy, definitely, for sure there is an interconversion, but charge is different property. So I think.
Yeah, where I will, what I'll do is I'll try to, maybe if I have get a definite answer, I will post the
Yeah.
answer in the
So if yeah. So as you
YouTube channel.
mentioned
Yeah.
that, yeah, as you mentioned that we as a researcher, we are confined to our one particular field and we are expert in that field. But you are always free to ask your questions, even if it's
Yeah,
not
no,
related to our
definitely.
work.
Yes, and this
We'll
is,
try
I
to,
think, a
yeah,
question
we'll
of
try to look for
fundamental.
the answer, and we'll try to.
Yeah,
Answer your questions in the comment section once the video is uploaded. So even in after the video is done, you can always come back in future, ask your question in the comment section. We'll try to answer them in future also.
yeah,
Even if we know the answer, we'll answer you right away. If you don't know the answer, we are good at looking for the answers. We are researcher, we read a lot, so that should not be a
yeah,
problem.
yeah. And this
So I
this
think,
question is a fundamental physics question. So
yeah,
I
so that's
I
different. Yeah, different
yeah,
genre altogether. I'll
yeah,
just ask one last question for you, and then I
yeah.
think we should be done. The question
Mhm.
I want to ask is that if someone want to become a researcher in astrophysics, how, what you want to tell them, what kind of course they can pick to become a astrophysics, to become a researcher in astrophysics,
Mhm.
or what you want to, how you want to guide
Yeah,
them?
yeah. I mean, so now, fortunately, now today there are so many astrophysics courses in India, because when I was doing my masters in physics, there were like not many who which were dedicated to astrophysics. But today in India, you can even do masters in astrophysics alone without like having a physics major. So that is something very nice, and that is what happens in other countries as well. But but in terms of that, I'm sure courses, to figure out which courses to take is very easy. You need to know astronomy, and you need to know physics, so there is many courses related to that. But in terms of interest, I would say that I would say to have a focus on both, like physics part of it, and because what happens is many people are fascinated by black holes or pretty pictures in the space. And you have to understand that being fascinated is nice as long as you are practically like
Yeah.
thinking it as a career opportunity. I'm not discouraging anyone, everyone should be fascinated I mean, I'm actually doing the inverse of being discouraged. I am telling you to look at things more objectively, which means that like to actually look at what people are doing, look at YouTube like documentaries about space and what people are doing, that are much more interesting when you like listen to something for 1 hour, instead of just thinking that, oh, space is so nice and I am just fascinated by that, so I should study space. So learning about space is very important to actually, because we don't know much yet, and there are a lot of people. When I went to astrophysics, I hardly knew much about it. So so it is interesting to know, it would be interesting to know. And also another important thing is that you have to, when you are like going towards master degree or towards PhD, it is important to understand that you are good in experiment or observation or theory, which is your field that you are more attracted to.
Mhm.
You may be wrong in your assessment, but still you should try to assess what you like more, because it's very different genre of working, how you work in labs and how you work on computational physics and how you work in observational astronomy. They're different, and they are very like interesting in their own ways. Say like talked about so much, but it was still physics. It has nothing to do with actual astronomers looking at telescopes, right?
Mhm.
I can bring a friend of mine who has the whole life only looked at telescopes. He would not be able to tell you the stories of how you analyze things like I was explaining, but he will be able to tell you incredible things of how you design a telescope observation and how you can find out objects in space, new objects in space. So you should, one who has a little bit of knowledge in physics and interested in that, it is a good thing to think about that, which fascinates him more, observations or theory or
Yep.
experiments.
So just to put these things in perspective, I think what you are trying to say is when you are young, you are a kid. I mean, if you are watching it as a kid, like middle school or high school kid, you can definitely, first of all, you have to fall in love with the field as such. Whether you want to become a cancer biologist, you want to become you want to become
Yeah,
astronaut, or you want to become, so those big picture you can look at and you can try to find where your interest lies. You could, it could be anything, like you can become artist if you
yeah, yeah, yeah,
love
yeah,
art.
exactly.
You can fall in art, or you love science. In science, what fascinates you. But as you grow little older, or you go to the from school, when you go to the college level, then you have to understand that the astrophysics is a one big field, and there's a lot of different kind of research which is
Aspects,
happening.
yeah.
Yeah,
Mm.
different aspect of it, whether being theory, or the practical part of it, observing the space. There is, then you want to go to the planets, extraplanetary studies. There are a lot of things. So then slowly you have to pinpoint that what and where your interest lies, and then you can watch a lot of talks about it. You can read some papers.
Yeah,
You
yeah,
can,
yeah. I
yeah,
mean, you
and
don't
then
need to read papers also. As a student,
at least,
just
yeah,
like know the basic things. Even like
yes.
there are so many documentaries now today on YouTube, right? There are so
Mm,
many beautiful documentaries that helps a lot. Like you would know incredible amount of things that like just by watching those documentaries, and that is nice enough to grow an
Yeah, so
interest.
that was one of the idea of this show, was just not only talk about this field as such, also give some shed on the kind of research people do in this field. Like I had no idea about what people do in
Yeah.
NASA, like how they do research. Obviously, there are different departments and they have
Yeah.
different kind of research.
Obviously, I did not give you like an entire story of NASA because
No, 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 no. I'm not talking about NASA or
what
European
I
Space
talking
Agency as such,
about,
but astrophysics in general. So I was always fascinated to know what people
yeah,
do. But now I understand that there are different sections, there are different departments, there are different part of it, and they have their own way. They have their own discoveries they are doing. Their own way to contribute to the overall project they're working on. And I was really, it was really interesting to know how you are using infrared spectroscopy to look at something which we cannot look using your regular telescope or visible light. So this was really interesting to know about it, and I'm really delighted that you gave your time, I mean your precious time, and um, you enlightened us with a lot of information. You shared real research, what you are doing, what people are doing around, and it was also a lot of general background about the astrophysics as such. So I think it was very interesting talk, and there was different dimension of it to learn from. So thank you so much for being with us.
yeah.
I wish you
Thanks.
all the best for your research. And
Yeah, yeah, yeah.
if
We
you
will
don't
be in touch, and
mind,
I mean, yeah, I will be in touch, and I really like your work, and I cannot even imagine how you can give so much effort to do this thing, and this is so incredible, so nice. Yeah,
but yeah, so I'm trying my best to bring a researcher from all different field and give some little bit idea of what people are doing around. If we motivate even one or two kids to become scientists, the purpose of the show will be solved. That's what I think. And with that, intention, I just make this video. But viewers, it's your responsibility to share it with as many as students you can, so that most of like many students get benefited from this show and they learn. It's absolutely free show. Just share with your friends and ask more and more students to watch the show. With that, I'll end today's session. If you have any question, guys, ask in the comment. We'll try to answer them. And all the best to you for your research. Thank you so much
yeah,
for
yeah,
being with me.
sure. Thank you.
Bye
Yeah,
bye,
bye,
guys. Take care.
bye, bye.